Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Atomic Force Microscopy AFM from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First, we will discuss the working principles of AFM along with its operating principle. Second, the AFM imaging modes, that is static mode, lateral force mode, dynamic mode or amplitude modulation will be discussed. Third, we will discuss about the piezo response force microscopy with its working principle. So, students, let us start with the basic introduction about the module. Ferroelectrics are the subclass of piezoelectrics, namely the materials that experience mechanical deformation under the applied voltage or charging under mechanical force. So, ferroelectrics exhibits a wide range of functional properties, including high and switchable electric polarization, strong piezoelectricity, high nonlinear optical activity, outstanding pyroelectricity, and notable nonlinear dielectric behavior. So, these properties are indispensable for the applications in numerous electronic devices such as sensors, actuators, IR detectors, microwave filters, and recently non-volatile memories, to name a few. Due to this unique combination of properties, researchers and engineers, they have been focusing on visualization of ferroelectric domains, areas with unique polarization direction at different scales. So recent advances in synthesis and fabrication of micro and nanoscale ferroelectrics brought to life new physical phenomena and devices that needs to be studied and understood at this scale. As structure dimensions are getting smaller and smaller, ferroelectrics exhibits a pronounced size effect, manifesting itself in a significant deviation of the properties of low dimensional structures from their bulk analogues. So, in this sense, ferroelectrics are similar to magnetic materials, since surface energy cannot be neglected in small volumes, and long-range dipole interaction is significantly modified in reduced geometries. It also depends on whether a ferroelectric is confined in one, two, or all the three-dimension structures. So, to address the fundamental mechanism underpinning the functionality of ferroelectric materials and devices, domain structures and their evolution under bias have to be studied at the micrometer and nanometer scales. So, the rapid development of scanning probe microscopy and especially atomic force microscopy and piezo response force microscopy AFM and PFM has resulted in a fabulous advancement. In this area, as will be highlighted in this module after the short description of the method. AFM provides a 3D profile of the surface on a nanoscale by measuring the forces between the sharp probe less than 10 mm and surface at very short distance 0.2 to 10 nanometer probe sample separation. So the probe is supported on a flexible cantilever. The AFM tip gently touches the surface and records the small force between the probe and the surface. Working principles of AFM. The principle of operation of the AFM is very similar with that of the stylus profilometer. That is, here a sharp cantilever tip interacts with the sample surface, sensing the local forces between the molecules of the tip and the sample surface. As shown in this figure, this instrument is not a conventional microscope that collects and focuses the light. The word microscope has been associated with this instrument because it is able to measure the microscopic features of the sample. The most characteristic property of the AFM is that the images are acquired by feeling the sample surface without using the light. In this way, not only the sample topography can be recorded with good resolution, but also the material characteristics and the strength of interaction between the sample surface and the cantilever tip. Due to the fact that no light is involved in acquiring the sample properties, the AFM reaches a resolution far below the diffraction limit offered by the optical microscopy. Its resolution is limited only by the tip radius and the spring constant of the cantilever. The main components of the AFM are the AFM probe, a sharp tip mounted on a soft cantilever, the optical lever that measures the cantilever deflections, the feedback loop that allows for monitoring the interaction forces between the molecules on the tip with the ones on the cell surface, the piezoelectric scanner that moves the tip relative to the sample in a 3D pattern, the conversion system from raw data acquired by the instrument into an image or other useful display. Let us now discuss the operating principle of the AFM, which is depicted in the following schematic. The heart of the AFM lies with the cantilever tip assembly that interacts with the substrate. This assembly is also commonly referred to as the probe. The tip interacts with the substrate through a raster scanning motion. The up-down and side-to-side motion of the tip as it scans along the surface is monitored through the beam deflection method. The beam deflection method consists of a laser that is reflected off the back end of the cantilever and directed towards a position-sensitive detector that tracks the vertical and the lateral motion of the probe. So the deflection sensitivity of these detectors has to be calibrated in terms of how many nanometers of motion corresponds to a unit of voltage measured on the detector. So the probe can also be mounted into a holder with a shaker piezo, which provides the ability to oscillate the probe at a wide range of frequencies, typically between 100 Hz to 2 MHz, enabling the dynamic modes of operation in AFM. So the dynamic modes of operation can be performed either in the resonant modes or in non-resonant modes. Let us now discuss the static mode of AFM imaging. So the static mode or the contact mode is the original and the simplest mode to operate an AFM. In this mode, the probe is in continuous contact with the sample while the probe raster scans the surface. In other words, the probe drags across the sample. The most common configuration of static mode is to operate it in the constant force or deflection feedback mode. In this mode, the cantilever deflection is the feedback parameter. The cantilever deflection is set by the user and is related to how hard the tip pushes against the surface so that the user controls how gentle or aggressive the interaction between the probe and the sample. Static mode can also be operated in constant height mode, where the probe maintains a fixed height above the sample. There is no force feedback in this mode. Constant height mode is typically used in atomic resolution AFM, though it is uncommon for other AFM applications. Finally, there is a configuration known as error mode. This mode is operated in contrast force mode. However, the topography image is then further enhanced by the addition of the deflection signal to the surface structure. So, in this mode, the deflection signal is also referred to as the error signal because the deflection is the feedback parameter. Any feature or morphology that appear in this channel is due to the error in this feedback loop, or rather due to the feedback loop needing to lock in to keep the deflection set point constant. In static mode with constant force, the output consists of two images: height, Z topography, and deflection or error signal. So static mode can be useful. Simple imaging mode, especially for robust samples in air that can handle the high loads and torsional forces exerted by static mode, but also surprisingly for more delicate samples in liquid, as long as the force can be controlled below 100 piconewton. Let us now discuss about the piezo response force microscopy. Piezo response force microscopy (PFM) is based on the mechanical deformation of the sample due to converse piezoelectric effect. The application of the electric field leads to thickness changes and or to shearing of the material depending on the direction of the electric field together with the piezoelectric tensor elements. So, to address the fundamental mechanisms underpinning the functionality of ferroelectric materials and device, domain structures and their evolution under bias have to be studied at the micrometer and nanometer scales. So, the rapid development of scanning probe microscopy and especially piezo response force microscopy (PFM) has resulted in a fabulous advancement in this area, as it will be highlighted later after the short description of the method. Let us now discuss the lateral force mode. This mode, or the frictional force mode, is a form of static or contact mode. In this type of mode, the imaging is exactly as it is in the static mode, except the cantilever scanning motion, which is generally performed perpendicular to the axis of the cantilever as opposed to a freedom of scan rotation for conventional static mode. The schematic of lateral force mode scan configuration is shown in this figure. This mode is particularly effective for measuring the friction of a surface, as the side-to-side twisting of the cantilever by torque is measured as the probe raster scans along the surface. Lateral force measurements can be converted to frictional force through calibration of the torsional spring constant of the cantilever. When operating in lateral force mode, it is important to be aware of topography that can convolute the lateral force signal. This is because changes in topography will incur a torsion onto the cantilever as well. In order to account for this topographic convolution, frequently lateral force images are collected both in forward and reverse scan direction and then subtracted from one another. Let us now discuss the dynamic mode, amplitude modulation. This mode refers to a collection of AFM modes in which the cantilever oscillates at a high frequency or closer to resonance. A specific kind of dynamic mode is referred to as the AM-AFM, which is the most common AFM imaging mode. In AM-AFM, the amplitude of oscillation is the feedback parameter. Other dynamic modes have different parameters for feedback such as frequency or phase for frequency modulation and phase modulation. AM-AFM is also referred to as the tapping mode or intermittent contact mode by other vendors. As an imaging mode, amplitude mode, modulation mode basically offers several key advantages because it operates at resonance, interacts with the sample as the probe taps along the surface. It is a gentle interaction with the surface relative to static imaging modes that preserves the sharpness of the tip. In this mode, the cantilever is generally driven with a shaker piezo and starts vibrating at the excitation frequency. By sweeping the frequency across a suitable range, the peak in the frequency spectrum, as shown in this figure, corresponds to the resonance frequency of the cantilever can be found. The cantilever is then driven with a sinusoidal motion at a fixed excitation energy, and it behaves as a damped spring or single harmonic oscillator. As the oscillating cantilever is brought closer to the surface, the cantilever cannot oscillate at its full amplitude anymore, and the amplitude of oscillation is reduced as shown in the schematic over here. So this amplitude reduction is the source of feedback. The user sets an amplitude based on the type of interaction that is desired. The changes in amplitude are caused by changes in the resonance frequency of the cantilever during interaction. In most of the real cases, the studied sample contains random oriented polycrystalline grain structure, often with non-zero lateral components in its piezoelectric tensor. In this case, the detected vertical PFM signal is no longer only proportional to D31 but also dependent on the D33 and D55 components. For example, the vertical PFM amplitude would no longer be delta Z0 equal to D33 V0. Instead, it would take the form delta Z0 equal to D33 V0 equal to D33 plus D55 sine square theta cos theta minus D33 cos square theta multiplied by V0, in which theta is the part of local orientation map between the lab coordinate system and the crystal coordinate system of the sample. Nevertheless, if both the vertical and the two lateral components of PFM signal are obtained on the sample location, either the intrinsic sample piezoelectric constants Dij or the local orientation map theta, phi and psi can be extracted from such data. So in a word, 3D PFM has opened the possibility of a complete 3D reconstruction of the polarization vector of the studied sample at nanometer scale. So the common applications of PFM includes the local characterizations of electromechanical properties of materials, including detailed domain mapping and study of domain switching dynamics, testing of micro and nano electromechanical devices, for example, piezoelectric actuators, transducers, and MEMS, electro-optical devices, and non-volatile memories components, that is FERAM devices, addressing their reliability issues such as electromechanical imprint, fatigue, and dielectric breakdown. So, which is exploring the local and the global relationship between the polarity and other material properties on novel polymer and bioengineered materials based on detailed nanoscale structural and electrical characterization of such materials. Let us now discuss the working principle. From the day that AFM was introduced to the contemporary research frontier, new modes and applications have emerged with unprecedented speed, allowing this versatile tool to look into ever increasing aspects of local material properties at nanometer scale. PFM is one such novel mode which has gained increasing recognition for the unique information it can offer on the electromechanical coupling characteristics of various ferroelectric, piezoelectric, polymer, and biological materials. In PFM, a conductive AFM tip is brought into contact with the surface of the studded ferroelectric or piezoelectric materials, and a preset voltage is applied between the sample surface and the AFM tip, establishing an external electric field within the sample. So, due to electrostriction or inverse piezoelectric effects of such ferroelectric or piezoelectric materials, the sample would locally expand or contract according to the electric field. Now, if we'll take an example, if the initial polarization of the electrical domain of the measured sample is perpendicular to the sample surface and parallel to the applied electric field, the domains would experience a vertical expansion. Since the FM tip is in contact with the sample surface, such domain expansion would bend the FM cantilever upwards and results in an increased deflection compared to the status before applying the electric field. Conversely, if the initial domain polarization is anti-parallel to the applied electric field, the domain would contract and in return results in a decreased cantilever deflection as shown in this figure. So, the amount of cantilever deflection change in such situation is directly related to the amount of expansion or contraction of the sample electric domains and hence proportional to the applied electric field. If the applied voltage contains a small AC component, the inverse piezoelectric response from the sample would result in sample surface oscillation in the same frequency as the applied AC voltage. In the case that the sample is an ideal piezoelectric crystal, its polarization would be related to the applied mechanical stress by the following equation, that is Pi equal to Dijk sigma Jk. Here Dijk is the rank 3 piezoelectric tensor of the material. For such materials with tetragonal crystal structures, these piezoelectric tensor can be reduced to the following form. Now here under the applied AC modulation voltage, V equal to V naught cos omega t, sample surface vibration would take the form delta Z equal to delta Z naught cos omega t plus phi. with the vibration amplitude delta Z naught equal to D33 V naught and phase phi equal to 0 if the sample domain polarization is oriented parallel to the applied electric field and out of phi equal to 180 degree if it is oriented anti-parallel to the applied electric field as shown in this figure. Such oscillation would be directly reflected in the amplitude and the phase signal of the AFM probe contacting the surface and can be read using a lock-in amplifier. So in a typical PFM imaging, the applied AC voltage is said to be much lower than the coercive bias for sample domain switching. So to avoid the alternation of the local domain structure of the studied sample, if such criterion is met, the phase contrast generated in PFM imaging will be reflect the domain polarity in different sample locations while form the magnitude of the amplitude signal local piezoelectric coefficient of the sample can be extracted. So this figure shows an example of such PFM amplitude and phase images obtained on PZT-5H sample as can be observed in the circled portion. 180-degree phase contrast is evident in two adjacent domains in the PFM phase image, and the domain wall between them can be observed with the reduced amplitude in the PFM amplitude image. Also, the upward and downward oriented domains have induced a PFM amplitude with similar magnitude, indicating the material property is relatively homogeneous in the studied sample. So, for a more complicated sample domain, orientation containing not only the components perpendicular to the surface in contact with the AFM tip, but also the components along with different directions within the sample plane, vector PFM will also affect, but along with the different vertical and two lateral channels can provide more complete information. Let us say, for an example, to obtain the D15 component of the piezoelectric tensor in tetragonal piezoelectric crystals, we need to measure the lateral components of AFM tip vibration proportional to in the plane sample surface displacement as shown in this figure, which would take the form delta L equal to delta L naught cos omega t plus phi with the vibration amplitude delta L naught equal to D15 V naught. Now notice over here, if a DC bias is applied between the tip and the sample in conjunction with the AC voltage, both the in-plane and out-of-the-plane electromechanical response of the sample are also functions of this applied DC voltage. So students, let us summarize what we have learned in this module. First, the working principle of AFM along with its operating principle was discussed in detail. Second, the AFM imaging modes, that is static mode, lateral force mode, dynamic modes, they were all discussed in detail. Lastly, we discussed about the piezo response force microscopy, PFM, along with its working principle. Thank you.